It's rush hour. Pick your city. Hundreds, no thousands of vehicles are traversing the highway on their way home from work. Many of the cars, SUVs, trucks, and/or vans only contain one occupant, the driver. Not the most efficient use of fuel, is it? Yet this scene is playing on repeat over and over and over again around this planet. What effect is all of this traveling having on the biosphere? Is the CO2 these vehicles are emitting changing the composition of the atmosphere? Is that change contributing to an increase in average global temperature? If so, what will this increase mean for our children? How about their children, or their children's children? These are some of the key questions to which I'm trying to find answers. Are you ready to join me on this journey? Let's go. Empathy is a human superpower. It sparks our curiosity, engages our compassion, and animates our connection to all living things. Let us journey together towards understanding as we sail through space on this amazing ship we call Planet Earth. This is the Empathic Ecologist. Why should I care? The answer to this question might seem obvious to some, but it still begs to be asked. If you've spent even a little bit of time reading social media feeds over the past 6 years, you have seen someone advocating for a cause. Be it Black Lives Matter, Me Too, MAGA, or marriage equality, it seems everyone has something they care about. Oh yeah, and don't forget COVID-19. No joke. At some point during the pandemic, I noticed people beginning to talk about compassion fatigue. Simply put, empathy requires energy, and each of us only has so much of it to invest. So why should we invest any of it in caring about climate change? One word: survival. If the planet is indeed warming at the rate I have read about in my early research, then future generations of Americans may very literally be facing a struggle for survival. Those of us who are at least middle class or above have no idea what it feels like to face starvation. Case in point, if I'm hungry for just an hour or two, I can get cranky, even hangry. I have no clue what it's like to look in the mirror and see an emaciated, skeletal face staring back at me because I have literally had nothing to eat in weeks. Get that picture in your mind. Okay, now imagine it happening to your grandkids. Make it personal. What if temperatures get so high that our crops just start dying off? That shit could happen. Am I just being an alarmist? I don't know. That's what I want to find out. So, here goes. Let's dive in to the data. According to NASA's Earth Observatory, quote, most of Earth's carbon, about 65,500 billion metric tons, is stored in rocks. The rest is in the ocean, atmosphere, plants, soil, and fossil fuels, unquote. That is, to put it mildly, a ton of carbon. See what I did there? All those carbon atoms are moving in a constant cycle between land, atmosphere, and oceans. This is what's known as the carbon cycle. To illustrate, let's take a look at this diagram of the fast carbon cycle, which has been adapted from the U.S. Department of Energy's Biological and Environmental Research Information System. The yellow numbers indicate natural fluxes in carbon levels, while the red numbers indicate human contributions. Numbers in white represent stored carbon. All are measured in gigatons. If you turn your attention to the top left corner of the diagram, we will begin by looking at the natural downward part of the carbon cycle. Approximately 120 gigatons of carbon are transferred from the atmosphere to the biosphere, which is where we live, by the way, via processes such as photosynthesis. Organisms containing carbon, plants, animals, and the like, die and decompose, transferring their carbon into the soil, which stores approximately 2,300 gigatons of carbon. If we go a little deeper, below the soil we can find fossilized carbon, primarily in the form of coal deposits. This adds up to roughly 10,000 gigatons of stored carbon. Leaving the land for the Earth's ocean, we observe that approximately 90 gigatons of carbon are transferred from the atmosphere to the oceans each year. Some of this carbon, about 2 gigatons, combined with the carbon contained in organisms which have died in the oceans, whales, dolphins, octopi, etc., travels all the way down to the ocean floor, where it becomes a part of the sedimentary level. Reactive sediments store about 6,000 gigatons of carbon. And we are finished with the downward portion of the cycle. Now on to the carbon which travels up. Starting back on the left of the diagram again, we see that plant respiration accounts for 60 gigatons of carbon release into the atmosphere each year. Microbial respiration and decomposition contributes another 60 gigatons. The ocean's surface level, which stores 1,000 gigatons of carbon, releases approximately 90 gigatons of that carbon into the atmosphere. Now we come to the human contribution. It is important to note that, quote, any change in the cycle that shifts carbon out of one reservoir puts more carbon in the other reservoirs, unquote. So says NASA's Earth Observatory. This is why we humans are responsible for 2 gigatons of carbon per year traveling back down to the biosphere and another 3 gigatons into the oceans. Since we are currently pumping about 9 gigatons of carbon per year into the atmosphere, this means that a good portion of what we pump out remains in the atmosphere itself. According to Lawrence Krauss in his book The Physics of Climate Change, this carbon will remain there for a long time. So, if our carbon emissions are indeed inducing climate change, this means that the current mean temperature levels will remain artificially high even after we have stopped pumping carbon into the air. But that leads me to my next question. So, are we causing climate change? In other words, are the carbon emissions that we humans are pumping out into the atmosphere, we just talked about this in the last segment, are those gigatons of carbon that we're pumping into the atmosphere affecting the composition of the atmosphere in such a way that it's artificially raising the temperature on the Earth? Now, I will say I have a lot of science yet to get to, and it will be a while before I understand the physics on a level that I would like to, so that my confidence isn't based solely on the basic conclusions that scientists have come to and trusting that they've gotten there honestly, that they've gotten there with the correct application of the scientific method. Not saying I'm in a position to judge that in any professional sense, but I do understand the basic scientific method, and I understand that sometimes other factors get involved with scientific endeavors, like it or not, such as politics, such as money, that can affect the outcomes, or just simply human behavior. Scientists are humans too, right? They don't always apply the method as diligently as they should. They're not perfect any more than you or I are perfect, so it behooves us to look into the science for ourselves, just as it behooves a scientist to look at the data carefully, to test and retest and test again his conclusions. So, getting back to the question at hand, are we causing climate change? And the short answer is yes. Now, the more conservative answer that I would give is it's plausible. And I say that because, once again, there's still a lot of science for me to study and look into before I can come to a firm conclusion. However, my initial conclusion is yes. My hypothesis is being confirmed thus far. So let's talk a little bit about why that's the case. So we talked about the carbon cycle in the last segment. We talked about how much carbon normally travels through the fast cycle, and that is basically in the course of an Earth year, how much carbon travels through that cycle, from the atmosphere down to the biosphere, from the biosphere down to, I think it's lithosphere, which is where the rocks, the soil, and all that. And from some of the plants down within the biosphere back up to the atmosphere. Decomposition is involved in all of that. You get into the ocean, decomposition of animals is involved in the carbon cycle. I believe carbon is absorbed. I know it's absorbed by the ocean. There's some degree to which I believe phytoplankton are involved in that process. I don't fully understand the science behind that yet, so I'm not going to speak to it. But so suffice to say, there is a normal cycle that carbon travels through on a yearly basis. And it seems obvious that we humans, through our carbon emissions, are interrupting that cycle, or we are artificially altering it by putting out, according to the chart that I looked up, and this is according to NASA, roughly 9 gigatons of carbon a year back into the atmosphere. 9 gigatons. And that's enough of a percentage increase to affect the composition of the atmosphere and to affect its ability to absorb ultraviolet radiation. So this is the key to understanding this. So you've heard some people, even someone as well known as Bill Nye and others talk about the greenhouse gas effect. So I'm sitting in my hot car right now. It has been out in the sun for 6-7 hours. I've been here at work most of the day. It's been sitting out here. It's hot. And the reason for that is what's literally the greenhouse effect. So the sun's rays come through the glass and heat up the interior of the car, but because all the windows are rolled up and because there's seals on the doors, now some of them are a little old, this is an old car, but most of the air is trapped inside here. There's not a lot of circulation going on between the inside of the car and the outside of the car. Therefore, the air molecules here, as well as the surfaces, of course, but the air molecules in particular are heated up by the sun's radiation. And even if all of the sun's radiation bounces back out, like I have a sunscreen that I put up on my window that's reflective, so it bounces some of those sun's rays back out before they have a chance to really get into the interior of the car, so at least it lowers the temperature a bit. But even those that are bounced back up, while it's here inside the car, it heats up the air molecules. Speaking of cycles and weather cycles, it's starting to rain right now. You can probably hear that. But it heats up the air, and the air gets hotter and hotter. And as long as that, it's not a vacuum in here, but as long as the air in here remains sealed in, it's going to remain pretty hot. The car itself will have to cool off significantly, which it will some at night, like overnight, as the sun is blocked, the car will cool down, and that will gradually cool down the air inside of it. But during the day, that's not much of that's going to happen. It's going to remain hot in here. The air is trapped. But the atmosphere doesn't work quite the same way. It's not the greenhouse effect, as it's been called, in relation to climate change, is not caused, and this is according to Lawrence Krauss, by the heating of air per se, because the air down here in the biosphere where we all live isn't trapped here. Technically speaking, there's a constant cycling and interaction that exists between the higher atmosphere, the lower atmosphere, between plants, animals, us. Like we're breathing, in a sense, the entire planet is breathing in and out, constant exchange. I know this is oversimplifying, but CO2, O2, CO2, O2, CO2, O2, breathe in, out. Right? The planet itself, and all the life on it is breathing. So when you throw in something that wouldn't normally be a part of that mix, so we dig down and we get into the coal that's down and we burn it for fuel, and it emits carbon into the atmosphere, or when we drill down and get oil, which is heavy in carbon, obviously, and then we burn it, we explode it inside of our cars, and then the exhaust from the exploding gasoline gets put back in the atmosphere, and it contains a large amount of carbon. Or when we burn plastics because we don't have the capacity to recycle them, and that black carbon just gets back up into the atmosphere, it changes the composition of the lower atmosphere. It increases the amount of carbon. And here's what's key, and Lawrence Krauss talks about this. that carbon absorbs ultraviolet radiation. And this has been tested by scientists, as I understand it, repeatedly. Now, I'll try to get you some links to the data. I recommend it, as a first foray into this world of climate change and science, read Lawrence Krauss's book, The Physics of Climate Change. It's accessible, but still challenging. He includes a lot of data, a lot of charts, so you can dig into it for yourself if you want to, but he explains it on the level of essentially a high school science student. That's essentially where he's aiming, which your average layperson like myself probably hasn't studied physics since high school. So that's where we're at, if we even remember half of what we studied. So it's successful. So read his book. But the key here is that as the sun's rays come down, and as some of them, not all of them, but some of them are reflected back up into space, and the atmosphere is, I suppose opaque might be the best word, but it allows the sun's rays to go back out, some of the sun's radiation to go back out in space, but there are certain gases and elements within the atmosphere that absorb ultraviolet radiation especially. Water is one, H2O. Obviously, you just look up, you can see clouds. I don't know if you can see them behind me, but I can look out right now and see clouds. Some rain just came from them. There's a lot of water vapor up there in the atmosphere. That water vapor absorbs ultraviolet radiation. And another element that absorbs ultraviolet radiation is carbon. And it's most plentiful in the atmosphere in the form of carbon dioxide, or CO2, as I understand it. And that CO2 absorbs ultraviolet radiation. That's part of the reason why it's not freezing or boiling down here. That's part of what regulates temperature. It traps in some of the radiation to keep things relatively warm here on this earth, so that when the sun is blocked by something, like say we're on the backside of the earth, we don't freeze to death, just like this, because we have no it's just the vacuum of space, and the radiation is blocked, so it's like fucking cold, excuse my French, but and then when we come back around and face the sun again, we burn to a crisp, or ash. It's like, no, the atmosphere helps to regulate some of the temperature, and it traps some of that ultraviolet radiation, which retains some of the heat within the atmosphere and within the biosphere, such that even when it's dark and we're on the side of the earth that is rotated away from the sun, there's not a massive temperature drop, maybe 20, 30 degrees, depending on where you're at specifically on the Earth's surface. But, where I live, it doesn't typically drop more than 20 or 30 degrees at night. And part of that is because the atmosphere traps ultraviolet radiation. But what happens if the atmosphere starts trapping more? Well, it's a fairly simple idea. Like, if the atmosphere has a higher ratio of either water vapor or carbon or both, makes sense, right? It's going to absorb more ultraviolet radiation, which, if that's part of what increases temperature down here and keeps ambient temperature at a certain level, if it traps more of it, it's going to gradually increase that temperature, right? That's the basic idea behind global warming. So it's different than the greenhouse effect, because it's not the trapped air that's being heated up per se. It's a little different than that. It's the trapped radiation that's been absorbed by the CO2, by the carbon, by the H2O in the lower atmosphere. Now, disclaimer, I'm not a scientist, as I've said many times, so don't just take my word for this. I am trying to learn this just as much as any of the rest of you who are watching this video. By the way, if you are watching, thank you. But that's basically it. Like, that's the initial conclusions I've come to. And reading Lawrence Krauss's book has already helped me understand the theories behind climate change better than I did before I picked it up. Been reading it on my Kindle. I recommend that format. And someday I want to get some actual copies, and like I want to donate one to my local library because they did not have one. That's where I looked first. So I want to buy one and eventually donate it to my local library, and actually I might donate one for each branch in my county because it's that important, and he explains it well, at least as I understand it. Now, I hope over the course of this 6-part series to be able to get a climate scientist, someone within that field. It's probably not going to be somebody famous. Sorry, like they're not likely to be interested in my channel, small as it is, although you guys can change that by watching and telling your friends about it. But for now, I'm probably going to have to reach out to someone I have a more direct contact with, but I'm hoping to find a scientist who is willing to give a perspective on Lawrence Krauss's work, because Lawrence Krauss is not an atmospheric physicist. He's not a climate scientist per se. He doesn't study the climate as part of his profession. His realm of physics, that the realm that he normally travels in, is a little different than that, and he says that up front. He doesn't pretend to be anything he's not. But because he is a physicist, obviously he's going to have a leg up on you or me, who haven't studied physics. Like, I haven't studied since 9th grade. So for me, that's 25 years? It's been 25 years since I studied physics academically. Yeah. So actually, I'm enjoying getting the science. It's hard. It feels like I'm back in school again, because with the exception that I'm giving this assignment to myself. All right, friends. So that's going to conclude this week's episode. Let me know what you thought of the experiments I did with some different formatting. I kind of combined. I've had some videos where I did just audio narration. So I wrote a piece and then I recorded the audio narration and put it over video. I've done that a few times, but I've never combined the two into a single video where I did both. So let me know what you think in the comments. Send me a direct message, send me an email, lifeisherevlog@gmail.com. You can also hit me up on Twitter, at EMP_ecologist. That's at EMP_ecologist. So my friends, fellow ecologists, thank you once again for watching. Tell your friends about it. Like, comment, subscribe, dislike. Let me know what you think. Liked it, didn't like it, agreed, disagree. I love your feedback. Peace, fellow humans.
Thank you for joining me for this week's episode of the Empathic Ecologist channel. If you would like to get in touch with me, you can follow me on Twitter at EMP_ecologist or on Instagram at ourbest_WS. You can also email me, lifeisherevlog@gmail.com. Be sure to check out the blog as well. The website is www.empathicecologist.blogspot.com. Until next time, my fellow ecologists, stay curious and be healthy.